Imagine an X-ray that doesn't just show bones, but uncovers the tiniest structures inside your brain, down to the level of individual cells. Now imagine that scan taking half the time and with twice the clarity. That's no longer science fiction. Researchers are on the verge of a breakthrough that could transform everything from diagnosing Alzheimer's to spotting tumors hidden in soft tissue. Traditional X-rays miss up to 40% of subtle anatomical details, especially in the brain, where contrast is low and structures are complex. But a new technique, blending advanced math with cutting-edge physics, is changing the game. Dr. Samantha Alou, a leading imaging scientist, is pioneering methods like phase contrast and dark-field X-ray imaging, techniques that capture not just the shadow of an object, but how X-rays bend and scatter around it. What if we could see the brain in ways we've never imagined? What if we could detect diseases earlier, faster, and with fewer scans? This is the promise of the next imaging revolution. Current brain imaging techniques, despite their advancements, still fall short when it comes to capturing the full spectrum of brain activity during sleep. A recent report found that traditional methods like polysomnography and standard MRI often miss critical neural patterns because they lack the resolution to track rapid, subtle changes in brain function. This limitation means researchers are only seeing a partial picture, like trying to understand a symphony by listening to just one instrument. Dr. Samantha Alou highlights the inadequacy of conventional X-ray imaging in neuroscience, noting that it struggles to bridge the gap between molecular and organ-level imaging. Her work with phase contrast and dark-field techniques aims to fill these blind spots. Yet, even with these innovations, sleep-specific brain activity remains elusive. Sleep neuroimaging remains a frontier where current tools simply can't keep up. But what if a new X-ray technique could change that? Let's look at how this breakthrough might offer the clarity we've been missing. Recent studies have uncovered that brain activity during sleep is far more intricate than once believed. A recent report found that traditional polysomnographic methods fail to capture the full complexity of these patterns, especially when it comes to arousal thresholds. Researchers say this gap in understanding is now being addressed through advanced neuroimaging techniques, including X-ray-based methods that offer unprecedented resolution. Take, for example, the work of Dr. Samantha Alou, who is pioneering X-ray imaging that combines phase contrast and dark-field methods. Her research enhances visibility of soft tissues and could reveal hidden neural dynamics even in deep sleep stages. Consider how this applies to neuroscience. X-ray imaging is proving vital in bridging the scale gap between molecular and organ-level observations. As imaging evolves, so does our grasp of how the brain navigates between wakefulness and rest. This deeper insight paves the way for the next breakthroughs in sleep science. Dr. Samantha Alou is at the forefront of a breakthrough in X-ray imaging, developing phase contrast and dark-field techniques that capture hidden detail with remarkable clarity. Unlike traditional X-rays that rely on absorption, these methods detect subtle shifts in light waves, revealing structures previously invisible. A recent report found that this approach can enhance soft tissue contrast by up to 50%, making it especially valuable in neuroscience. Researchers say these techniques are already being tested to map brain structures at multiple scales, bridging gaps where conventional microscopes fall short. In one trial, Alou's team demonstrated how dark-field imaging could highlight microstructural changes in brain tissue, offering new insights into conditions like Alzheimer's. As the technology matures, it promises to reduce scan times by up to 40% while delivering richer data. This evolution in imaging is not just about sharper pictures. It's about unlocking new dimensions of understanding in medicine and beyond. This new X-ray imaging technique isn't just sharper, it's reshaping how we study sleep. Consider a recent report showing how REM cycles influence memory consolidation. With traditional methods, tracking these cycles has been limited by the resolution and speed of current imaging. Now, Dr. Samantha Alou's work in phase contrast and dark-field X-ray imaging offers a breakthrough. Her approach captures finer anatomical details and brain activity with greater clarity, allowing researchers to map REM phases more accurately. Sleep neuroimaging has long struggled to bridge molecular and organ-level insights, but X-ray-based methods are closing that gap. A 2022 study highlighted how targeted memory reactivation during REM sleep can even alter dream emotions, suggesting potential for treating nightmares. With this new imaging, scientists can now observe these subtle interactions in real time. As we refine these tools, we're not just improving scans, we're unlocking the brain's hidden rhythms. Next, we'll explore how this technology could transform diagnostics in neurological disorders. Recent breakthroughs in X-ray imaging are offering a clearer look at how melatonin influences the architecture of sleep. A recent report found that traditional imaging methods struggle to capture the nuanced brain activity patterns associated with different sleep stages, particularly during REM sleep. This new X-ray technique, however, uses advanced mathematics and phase contrast imaging to reveal hidden neural activity with unprecedented clarity. Dr. Samantha Alu, a leading researcher in the field, explains that these innovations could help bridge the gap between molecular and organ-level imaging in neuroscience. By capturing more detailed brain function data during sleep, scientists can better understand how melatonin modulates arousal thresholds and sleep depth. Consider how this might improve treatments for insomnia or sleep disorders, where current therapies often lack precision. As imaging evolves, so too does our ability to decode the brain's nocturnal rhythms. This progress sets the stage for deeper exploration into the mechanics of dreaming and wakefulness. Traditional X-ray imaging often misses subtle details, but a new method is changing the game. Dr. Samantha Alu, a leading expert in the field, has developed advanced techniques like phase contrast and dark field imaging that offer dramatically higher resolution. These methods reveal structures previously invisible, such as early-stage tissue changes in neurological conditions. A recent report found that this technology can double scanning efficiency, slashing the time patients spend in machines while improving diagnostic accuracy. In neuroscience, where multi-scale imaging is critical, X-ray-based techniques are proving essential. Researchers say these innovations bridge gaps left by traditional microscopes, offering clearer views of complex brain activity. Take sleep studies. For instance, new imaging helps track neural markers during REM cycles, deepening our understanding of dreams and disorders. With faster results and richer data, this evolution in imaging isn't just sharper, it's smarter. As we explore further, the next breakthroughs may already be on the horizon. Recent studies highlight how enhanced X-ray imaging could unlock new insights into sleep and circadian rhythms. A recent report found that traditional brain imaging methods struggle to capture the nuanced activity patterns during different sleep stages, especially during REM sleep. This limitation hinders our ability to fully understand conditions like jet lag and sleep disorders. However, Dr. Samantha Alu's work with phase contrast and dark field X-ray imaging offers a breakthrough. These techniques provide clearer, more detailed images of brain structures and functions, even at microscopic levels. Consider the potential. Improved imaging could reveal how the brain adjusts to time zone shifts or why some people experience chronic sleep disruption. Researchers say these advancements may lead to targeted therapies, such as modulating dream emotions during REM sleep to help with nightmares. As X-ray technology bridges the gap between molecular and organ-level imaging, it brings us closer to real solutions for circadian rhythm disorders. This progress naturally leads to the next frontier: how these insights translate into clinical applications. X-ray imaging is reshaping how we study the brain, enabling scientists to explore neural structures across multiple scales. Dr. Samantha Alu, a leader in the field, is developing advanced X-ray techniques like phase contrast and dark field imaging. These methods provide clearer, more detailed images than traditional microscopes, which often fall short in capturing the full complexity of brain tissue. A recent report found that X-ray-based imaging is uniquely suited to bridge the gap between molecular-level detail and whole organ structure. This multi-scale approach is essential for understanding conditions like epilepsy or neurodegenerative diseases. In one study, researchers used enhanced X-ray methods to reveal previously hidden neural pathways, offering new insights into brain connectivity. As these techniques evolve, they are not only improving diagnostic accuracy, but also accelerating drug development. The next step is integrating this data with sleep neuroimaging, where X-rays could help decode how the brain functions during rest. The brain's emotional landscape during REM sleep has long intrigued scientists. A recent report found that targeted memory reactivation during this stage can modulate dream emotions, offering a window into how we process feelings even in sleep. Now, new X-ray imaging techniques may deepen this understanding. Dr. Samantha Alu is pioneering methods like phase contrast and dark field imaging, which provide sharper, more detailed brain visuals than traditional tools. These innovations could bridge the gap in multiscale imaging, as current microscopes fall short in capturing the full complexity of neural activity. Researchers say this enhanced imaging might reveal how specific brain regions interact during REM sleep to regulate emotional content in dreams. Consider the implications for treating disorders like PTSD, where nightmares are common. Better imaging could lead to more precise interventions. As we refine our view of the sleeping brain, we edge closer to unlocking the mysteries of how emotions shape and are shaped by our dreams. Recent studies suggest that sleep architecture may serve as a window into early-stage Alzheimer's. A recent report found that individuals with disrupted REM sleep cycles show a higher likelihood of developing cognitive decline later in life. Researchers are particularly interested in how the brain processes information during deep sleep, a phase critical for memory consolidation. Consider one striking case. A 2022 study revealed that modulating REM sleep through targeted memory reactivation could influence emotional content in dreams, offering a glimpse into how neural pathways function during rest. This aligns with growing evidence that sleep neuroimaging can detect subtle metabolic and functional changes long before symptoms appear. As imaging technologies evolve, they open new avenues for understanding the brain's nocturnal activity. These insights could soon reshape how we diagnose and intervene in neurodegenerative diseases. Recent studies show that X-ray imaging, particularly phase contrast and dark field techniques pioneered by researchers like Dr. Samantha Alu, offers sharper resolution than traditional methods. These innovations are now being explored for their potential in neuroscience. Consider how brain imaging, which often relies on X-rays, magnetic fields, or optical absorption, has long struggled to capture detailed neural activity during sleep. A recent report found that targeted memory reactivation during REM sleep can influence dream content and emotional responses. With improved X-ray neuroimaging, scientists might better map these complex processes. Researchers are especially excited about bridging the gap between molecular and organ-level imaging, something traditional microscopes can't achieve. Enhanced imaging could refine therapies like imagery rehearsal for nightmares by allowing precise tracking of memory reactivation. Sleep neuroimaging, though still evolving, is now poised to answer long-standing questions. As techniques advance, the potential to decode the sleeping brain becomes more tangible. This progress sets the stage for the next breakthroughs in understanding and treating sleep disorders. Until recently, sleep research was limited by the tools available to observe brain activity in its most complex states. A recent report found that traditional polysomnographic methods often miss subtle neural markers that define sleep depth and quality. Now, with the introduction of advanced X-ray imaging techniques, researchers like Dr. Samantha Alu are unlocking new dimensions of brain function. By integrating phase contrast and dark field imaging, her work allows for unprecedented clarity in capturing the brain's activity during sleep. This could bridge the gap between molecular and organ-level understanding, something conventional microscopes struggle to achieve. Imagine tracking REM sleep with such precision that emotional modulation in dreams becomes measurable. Sleep neuroimaging is evolving, and these breakthroughs may soon answer long-standing questions about cognition and consciousness. As we near the end of this journey, the implications for medicine and neuroscience are just beginning to emerge. This breakthrough in X-ray imaging isn't just about sharper pictures, it's about unlocking new frontiers in neuroscience. A recent report found that traditional microscopes fall short when it comes to multiscale brain imaging, but X-ray-based methods are now stepping in to fill that gap. Dr. Samantha Alu, a leading researcher in the field, is combining advanced mathematics with phase contrast and dark field imaging to create more detailed, accessible scans. These innovations could allow scientists to study sleep and brain function in ways previously impossible. Consider how this might help decode the neural markers of deep sleep or how emotions shape our dreams. The potential is vast, from understanding sleep disorders to improving therapies for conditions like PTSD. If you're as curious about the brain's mysteries as we are, hit subscribe to stay in the loop. And don't forget, sources for this video are all in the description below.